Hello, hi everyone. Now let's discuss briefly. You have this handout, of course, is tools for counting sample points, because we learned already before how to get the probability of certain events when we are dealing with equally likely outcomes in the sample space. All right, so but sometimes we will need some other techniques. So let's see, basic counting principle. Okay, suppose that we have two experiments are to be performed. Then if experiment one can result in any one of n possible outcomes, and if the second one results in n possible outcomes, then total there are m times n. So I roll a die. How many possibilities I have? 6. Then I roll a second die. Then I also have 6 possible outcomes, and that's why when I roll 2 dice, there are 36, 6 times 6 possible outcomes. If I roll 4 dice, then there will be, for each die I have 6, so then is the multiplication, and then I can do probability. But let's look at this quickly. So if I want at least 1, 3, so at least 1, 3 means 1, 2, 3, 4. But it's better to here. Every time I see at least one, I have to think, can I solve this problem using the complement of the event? So here, if A is the event at least 1, 3, the complement is no 3. And that is easy to compute. And that's why the probability, the number of sample points in the event A complement is going to be this one, where I don't have a 3. So it's 625. And then I have here the ones for the 4, 6. Okay, I can, of course, I can type this because I want this probability, and remember, probability is not money, so I want 4 decimal places, and that's why I write it like this. Now, permutations where order is important. So here what we have, what is a permutation? Any order arrangement of R objects. So the number of ways of ordering n distinct objects taking R at a time is denoted by this. Sometimes also I could put RPN. They don't have to be subscript and superscript, but superscript. But suppose we have n objects, there are n factorial, different permutations, okay? When I put all the objects, but then if I want less, we will see what happens. The number of permutations taking R at a time is going to be this product, all right? And this simplifies as this little manipulation for factorial. Remember, this is what factorials are all about. And we have in R the function factorial. So as you can see here, if I put on R, I have opening factorial, the 5 factorial, I get 120. Okay? So this is now for the number of permutations. So then look for these calculations, I will use then the product function, because I only want the first, n minus 1 all the way to n minus r plus 1. So we will see, for example, I have, let's say I have the 4 letters, and I want the different permutations when I pick 2 of these at a time. See that here we will have 12, okay? Because A, B, and BA are different. Order matters. So this is the thing. I have 12. If I want to pick 3 letters at a time, it will be 24. Okay? And this, by the way, this is how, I'm not going to list 24 of them in any case. Now, this is an example where we have the names of 3 employees are to be randomly drawn without replacement from a ball containing the names of 30 employees of a small company. The person whose name is drawn first receives $100, and the individual whose name is drawn second and third receives. So here it's important if your name is drawn first place, second. So permutation is what we have to do. So then this is the way I will want to do it, right? So see that I want permutation, taking 3 names out of the 30, but it's permutation. So this will be the formula, but I can get this, right? And as I say, n minus r, which will be 27 plus 1. So that's why I can get this using product 28, right? I can go to R and get the number like that and forget about the individual calculations. Now here, let's say I want to get the number of distinguishable permutation of the letter Hawaii. So what do we have here? 2 A's. I cannot distinguish this unless we were putting A1, A2. But the way it is, 2 are indistinguishable, and then the 2i as well. So here is a close, right? The theorem is I will get n factorial, how many letters I have, 1, 2, 3, 4, 5, 6, but I will divide by the fact that I have 2 A's and I have 2 I's. So that's why I get that. Let A, example 5, be the set of all sequences of 0s, 1, and 2 of length 12. How many elements are there? So 3 to the 12, right? Because for each spot, I have 3 possibilities. Then let A, all right. How many elements of A have? Exactly 6 0 and 6 1. So then I am looking with for restriction. The 0s are indistinguishable and the 1s. So then that's why I divide by that. And similarly then in part C. Now you are asked here, highlighted, study that example. Now, the second concept in counting is combinations. So it's like if I draw to that example that I have here, right? When I pick 2 letters, but order was important. I have these 2. In the number of combinations, the order is not going to be relevant. So this eliminates that, eliminates that, eliminates that, eliminates that. So I have already 4. So similarly, 5 and 6 is a lot less, right? Because order is irrelevant. Whether you get AB or BA, you are getting the letters. So it's a new concept. So let me get here the number of combinations of n objects taken r at a time is the number of subsets of each of size r that can be formed from n object. This number is denoted C for combination of n choose r, or n, we say n choose r. This is the typical notation, and we use in R choose n from n choose k. Very simple to calculate. The number of unordered, emphasizing in combination, order is irrelevant. Subset of size R choosing without replacement, okay? From n available items is n choose R. The without replacement is important because if I replace, that's a whole different story, right? Because then I always have, imagine choosing the 2 letters from those 4. If I always replace them, then I don't have the same number. I have more if I replace them. Okay. So the number of unordered subsets of R choosing without replacement from N is N choose R, right, notation, which it turns out to be similar to the number of permutations, but I divide, right? I divide by R factorial. So it's going to be less. These are relations. You can easily show them. This one, so N choose 0 equals N choose N equals 1. That's typical. And N choosing 1 is the same thing as N choosing N minus 1, which is N. And then we have that. So let's see here. In how many ways can 2 math and 3 biology books be selected from 8 math and 6 biology books? So to choose the math books, I have 8 choose 2, and 6 choose 3 of selecting the biology ones. So the counting principle is by this many numbers, okay? That good. Now, this will help with the homework. You have 52 cards, and 7 are going to be drawn at random and without replacement. What is the probability that at least one of the cards is a king? So choosing 7 cards out of the 62 can be done in 52 choose 7 ways. Okay. Now we want at least one of the cards. You remember what I say? At least it's a hint that maybe consider that we are going to use the complement of at least one king is no kings, okay? And how do we choose no kings? So from the, there are 4 kings. So the remaining are 48 cards that are no kings. So from the 48, choose 7. And that's why probability at least one king is 1 minus the probability of no kings. So it's going to be 1 minus this probability. Choosing any other card divided by how many ways can we choose 7. Okay, you will read. So this thing, there is some problems that I added solution. So for example, if we have tossing a pair of dice, that's famous. For the combinatorial, this is what it means, okay? The probability that appearing on the numbers on the die, the sum equals 7. This will be the points in that, right? I see where the 7 equals 7. So P of A equals 36. We will come back to this situation immediately after when we do random variables, okay? Just look here, 7. This is 7. These are the outcomes in which the sum of the 2 dice equals 7. This one in the diagonal. Okay, so these are some examples for you to review problems from the board. You can study them, convince yourself that they are, and you can work on the homework.